Hey Jarvis. Hey Mycroft. Alexa. Hey Jarvis.
No cloud, no API calls, just a Raspberry Pi detecting 3 different wake words completely offline. Remember when we built an offline wake word detector on the ESP32 using TinyML?
Okay, Marvin.
You again. What now, Sham?
Something very similar is happening on our Raspberry Pi here as well. But this time, we will use OpenWakeWord, a lightweight wake word engine. Let's see it in action. OpenWakeWord is an open source wake word detection engine. My original plan was to compare it against Pico Voice Porcupine on the Raspberry Pi, but just before making this video, I learned that Pico Voice ended its free access for new users. So setting up a fair comparison wasn't really possible anymore. From what I have gathered, Porcupine is considered to be one of the best wake word engines out there. But for broke engineers like us, open source is hard to beat. So open wake word it is. The good news is that it's surprisingly easy to get started with. It supports both Onyx and TensorFlow Lite models and can run multiple wake word models simultaneously in real time. But what does that actually mean? Well, with OpenWakeWord, each wake word is packaged as its own model. Hey Jarvis, Alexa, Computer, Marvin, you get the idea. If you want to add another wake word, you simply load another model. That wasn't the case with the TinyML example we built on the ESP32. There, we had a single model with a softmax layer at the end that classified every audio sample into one of the categories: silence, unknown, Marvin. Think of it this way. In TinyML, one expert listens to an audio sample and picks the correct option from a multiple choice question. In OpenWakeWord, multiple experts listen to the exact same audio sample, but each expert is responsible for only one wake word. Their job is simply to answer, did I hear my wake word? Yes or no? Moving on, if you have followed the previous video where we interfaced the ICS43434 MEMS microphone with the Raspberry Pi, that setup becomes the foundation for wake word detection. One quick tip, always open ALSA mixer and verify the microphone gain before testing, as the gain settings tend to reset after every reboot. Or you can also use a mixture command to set the desired gain in the terminal itself. With that done, I've created a Python virtual environment for this project along with a simple script. Let me quickly give an overview of what it does. As we saw in the previous video, our ALSA device is named mic SV. When we inspected its hardware parameters, it was configured to output 48 kHz, stereo, 32-bit audio. OpenWakeWord, however, expects 16 kHz, mono, 16-bit PCM audio. So the first step is to capture the microphone data exactly as it comes from the hardware. We then convert it into the format expected by OpenWakeWord by downmixing the stereo channels into mono, converting samples to 16-bit, and resampling from 48 kHz to 16 kHz. Once the audio is in the correct format, only then we feed it to OpenWakeWord for inference. If you initialize OpenWakeWord without specifying any model parameters, it automatically downloads and loads all of its default wake word models. The prediction output is simply a dictionary where each key is a loaded wake word and its value is the corresponding confidence score. We compare those scores against a predefined threshold, and whenever a wake word crosses this threshold, a simple detection message is printed and LED assigned to that particular wake word is turned on. That's really the entire pipeline. Let's go ahead and run the script. Alright, it's listening.
Hey Jarvis.
Great, everything is working as expected. But technically, this still isn't a completely offline device because I am connected to the Raspberry Pi over SSH through my Wi-Fi network. To make it truly standalone, we will create a systemd service. This allows the script to start automatically every time the Raspberry Pi boots. The service itself is pretty straightforward. We give it a description, tell systemd to start it only after the audio subsystem is ready, and specify the working directory for our project. Then, we add a short 2-second delay to let everything settle after boot. Next comes the amixture command, which restores the microphone gain. As we discussed earlier, ALSA has a habit of forgetting the mixer settings after a reboot, so this makes sure the microphone is ready to go. After that, we specify the Python executable from our virtual environment along with the path to the actual script. Finally, we enable automatic restart. So, if the script ever crashes because of some unexpected reason, systemd simply starts it again. And that's it. A pretty simple service, but it makes the project behave like a proper embedded application instead of something that has to be launched manually. Now let's enable the service, shut down the Raspberry Pi, and let me also switch off my Wi-Fi router. So there's no SSH, no network, nothing at the moment. Time to power the Raspberry Pi back on. Wait for the boot sequence.
Hey Jarvis. Hey Mycroft. Alexa. Hey Jarvis. Hey Mycroft. Alexa.
Now that is what I call actual offline wake word detection. And that's it. We now have a Raspberry Pi that can continuously listen for multiple wake words and react to each one independently. That too, completely offline. If you found this video helpful, consider giving it a thumbs up. It really helps the channel reach more fellow engineers. And make sure you are subscribed so you don't miss the next part in this audio series. As always, thanks for watching and I'll see you in the next one. This is Avinashee Tech, signing off.